Good morning, students. Today we are going to learn on continuation of synchronous motor performance. In last class we have seen the mathematical equations for synchronous motor. When synchronous motor overexcited, underexcited, normal excitation, then what is the armature current drawn from supply? As we know that when rotor is excited, normal excitation takes place. Stator will draw the current from three-phase AC supply in phase with the rated voltage. Armature current and voltage are in phase, then cos phi equal to 1, power factor 1, that's UPF. The motor under low external load, minimum load on rotor, motor is normal excited, the motor draws a unity power factor current from the input supply. In this case, we know that equations also, the back EMF calculated, that is equal to root of terminal voltage, square of the terminal voltage plus square of the resultant voltage minus 2 into voltage into ER into cos theta minus phi in case of lagging power factor. So, in normal excitation, so here the phi is power factor, phi becomes to the 0, then so whatever the cos theta minus phi becomes to theta only. Under normal excitation, the back EMF induced in the rotor is equal to square root of V square plus ER whole square minus 2 into V into ER into cos theta. At the same time, the sin alpha is equal to ER by EB sin theta. So, let us see that one with the help of some figure. You can see it. Last class we done this all. The first case here, this is the first case, the motor runs under excitation, under excitation. That means in this case the terminal voltage is greater than EB, back EMF developed in the stator. During this period, the armature current lagged by voltage some angle phi, that is we say lagging power factor. This is the armature current, this is the voltage. At that condition, the back EMF in the motor is equal to square root of we are going to square root of terminal V square plus resultant ER whole square minus 2 into V into ER into cos theta minus phi. By applying cosine rule in this condition, under excitation condition, so we are going to get EB, back EMF, and at the same time sin alpha also is equal to ER by EB into sin theta minus phi. So, if the motor is overexcited, DC supply is given more, then in that case the current which is drawing from the supply is leading power factor. Then this is the voltage, current goes to this direction I. Then this is a phi, leading power factor. At that condition, the back EMF in the motor is equal to square root of V square plus ER square minus 2 into V into ER into cos. Now this is the angle between the voltage and ER is equal to theta plus phi. This is the changes only. Due to this back EMF, the current drawn is leading power factor. At that condition, if we want to know the sin alpha, then this is a formula, ER by EB into sin theta plus phi under overexcited condition. Generally, the synchronous motors used in all industries to nullify the lagging power factor. 70% of the motors used in any industry is the induction motors, whether single phase induction motors or 3-phase induction motors. The induction motors always draws the lagging power factor. Then power factor value, instead of 0.85, it may be decreased to the less than 0.85 PF. But discom people, there is restrictions. It should be maintained 0.85, otherwise there is a penalized by some lakhs of rupees. So the industrial people, they will install the capacitor banks in addition to the synchronous machines, synchronous motor. The synchronous motor runs under normal less than rated load but overexcited condition. Then the current which is connected in industry to our synchronous motor draws the leading power factor. The remaining motors lagging power factor, this motor is the leading power factor, and both is combined, then at least the power factor may not be unity power factor, it may be 0.85 or 86 they will maintain. They escape from the penalty from discom people. Now you can see under normal conditions, similarly in the normal excitation, another equation here you can see. So here same thing, here under normal condition the current, voltage are in same phase, power factor becomes 1. Then so here the VR whole square plus ER whole square minus 2 into V into ER into cos theta is the back EMF in that machine. Then sin alpha is equal, this one sin alpha is equal ER by EB into sin theta. So by knowing these factors we are going to calculate. So what is the load angle under excitation condition, what is the power factor, or what is the internal angle. So we are going to calculate based on given factors. These all things we derived in last class with help of the phasor diagram also. Just is a recap. Now at the same time we also seen the J notation. While in calculating we require the J notation. So this is the voltage, normal voltage, and this is a EB, and result of this one we are going to get that ER, and correspondingly the armature current. This is a lagged by the V, some angle of phi, and this is a lagged by the current by angle of theta, and EB is goes and alpha angle. So we have seen last class. Now for calculation purpose, here the applied voltage taken as a reference V at an angle of 0 degrees. Now ZS, synchronous impedance, that is equal to RA plus J of XS. We taken this synchronous impedance. Now the current we taken here, this direction IA. So IA at an angle of plus or minus phi. This is angle phi. That phi means here whether the phi is a positive phi or negative phi. So here the negative phi indicates for lagging power factor motor. That means under excited condition, so IA is equal to IA at an angle of minus 5 degrees. If over excitation condition, that becomes to the positive value. You can see here IA at an angle plus 5. Then EB for phase, we are going to this one V minus IA ZA. This is supply voltage minus IA ZA, we are going to get what is the back EMF induced in the motor. Now, so here EB at an angle of alpha. This is at angle of alpha. So these are vectors. That means V taken as a reference, I as a lagging based on the excitation and load current, and ER is the theta and EB is the at angle of alpha. These are terms generally we required. And last class we also consider this thing. Now coming to the power. So power flow diagram, the power equations. As we know that, so motor input supply is given here, and from motor input it develops some amount of the energy. That energy is a gross mechanical power developed in the prime mover. This is the input, this is prime mover. But in between there is a copper losses takes place in stator winding and rotor winding. Total input minus the stator copper losses, we are going to get that stator output, nothing but the gross mechanical power developed in the machine. From mechanic, that is a stator output is nothing but rotor input, that is a PM, the mechanical power developed in the machine. And after reaching this power and rotor and as also the excitation, iron losses, friction and windage losses. So we have to subtract, and some part of the copper losses also we have to subtract from the input, rotor input. Then so we are going to get final net output. So net output in this case is a mechanical output. Same thing we have seen last class. Now here you can see power out is equal to prime mover input minus iron losses, friction and windage losses and excitation losses. Finally, we are going to the P out. Motor output is the P out. Rotor input is equal to PM. From that one, we are subtracting the inherent losses. We cannot avoid this iron losses and friction and windage losses and excitation losses. So this equations is required for knowing the performance of machine. Now you can see another also, the power developed by synchronous motor. So analysis purpose, the mechanical power developed for phase is equal to, here is a PM. The equation, general equation, that is equal to back EMF into voltage divided by synchronous impedance into cos theta minus alpha minus EB square by ZA into cos theta. This is a basic formula generally used in synchronous motor, but there is no derivation for you. So we are going to write directly. So whatever the stator output is equal to the back EMF developed in the motor and applied voltage, product of these two divided by synchronous impedance into cos the theta minus alpha minus the back square of the EB by ZA and cos theta. So If the motor resistance value is very less, suppose armature resistance value is a very low as compared to the XL in impedance, synchronous reactance, then we are going to neglect this value. So whatever the ZA equal to and XS, or we can write the XA. Then once this is known, we know that theta is equal to tan inverse of XS by RJ. Now we are neglecting this value, so we are going to get that theta is equal to 90 degrees maximum at that condition. So substituting this value in the equation, the cos theta is goes to 0 value, and this cos 90 minus alpha is equal to sin alpha. We are going to sin alpha. Then we are going to get this value will goes to 0. Then Pm is equal EbV by Za into sin alpha. That is a simple formula we are going to get here. Okay, so you have to remember this formula. When if resistance is neglected, we are going to write this one. The mechanical power developed in the rotor is equal to back EMF, product of back EMF and terminal voltage divided by XA into sin alpha. If resistance is not neglected, then we are going to use this formula. So this also we discussed in last class. Now coming to our topic. So now we are going to do the calculations based on given formula. Let us see the few problems based on what we have discussed in this class. Now you can see one problem. Here one problem is given. Here the synchronous motor. Now what is given? A 3-phase supply, 400 volts 3-phase supply is given. When it is connected to the star, synchronous motor has a resistance of 0.3 ohms per phase and synchronous reactance here Zs is given, R plus J of Xs is given. This value is given. The motor is operating at a power factor, phi is given. So cos phi is given 0.8. Leading here is given the leading, PF leading. Operating at a 0.8 PF leading. A line current of 80 amperes is given. So IA also is given 80 amperes. Determine the value of generated EMF, that is equal to, here you are going to find that what is the EB, generated voltage is the EB. Generated voltage EMF per phase, and also it's the line current. So you are going to determine the value of generated EMF per phase and also its line current. So here the problem is given. What they have given, once again you can listen. This is the motor. When 3-phase supply input is given from the 3-phase supply, once it is connected, it drawing a current of load current nearly 80 amperes at a power factor of 0.8 PF lead. The loading current nearly so much 80 amperes at leading power factor. Then its stator constants as given, Zs is given. So here IA is given, armature current, and Zs is given. From this one we are going to calculate. So each and dear students, so here given the 3-phase, better to convert each value in per phase value. For phase you are going to calculate. After that you are going to convert into 3-phase because it is connected star. In star connection, the current is same for the line current and phase current, but whereas the voltage we are going to reduce line current by √3 times. Okay, so these are the basic data is given. Based on this one, we are going to calculate the EB. What is the formula? EB formula, you know that. So EB is equal to under root of, what is the formula? EB, that is equal to V square plus ER whole square minus 2 into V into ER into cos and over excitation is the cos theta plus phi. So, theta plus phi over excitation, leading power factor. So here we are going to calculate. So power factor is given, phi known value, and theta we are going to calculate tan inverse of R by XS. This also we known, theta also known. So these terms we known, and V is already given in this one, and ER we are going to calculate. So ER is equal to resultant voltage is equal, we know that IA into ZA. So IA is given, armature current is given, ZA we known this value. So substituting armature current and impedance value, we are going to ER. Once we are going get the ER, applied voltage V is given and ER is given. So all values are, by substituting we are going to EB, that is the required value. Okay, so remember this thing. So dear friends, here I want to know that EB. EB is equal to under root of V square plus ER whole square minus 2 into V into ER into cos here theta plus phi. Okay, theta plus phi, because leading power factor. This is the basic formula already we known. Now EB I want to know. I know the V supply voltage is given. ER is equal, I can write it. So ER is equal to IA into ZA. Z is given. Z A is given, ZS or synchronous impedance, R plus J of XS. Resistance is 0.3 for phase, XS is given 2.4 XS. From this one I am going to calculate synchronous impedance. So this synchronous impedance, load current also given 80 amperes. So from this one I am going to calculate the ER. I know the V, I know the ER. At the same time the ER, the cos theta plus phi. Phi is equal, cos phi is given. Cos phi is equal, how much is the leading? 0.8 leading. So from this one I am going to calculate the cos inverse phi is equal, we are going to get the phi value. Next I want the theta. Theta is equal tan inverse of x by r. So you know this value, you know this value. So theta also we are going to get. So what is unknown here? This known, this known, and this known, this known, and this known, and this known. Simple substitution of this value, we are going to get EB value. Now lastly the line current. So here, phase current, you are going to calculate the phase current into line current star connected, similar value. So this is a basic idea. Let us do this problem. Here three phase star connected, given data, 3 phase star connected synchronous motor, supply voltage is equal to V well, supply voltage is equal, line voltage is equal 400 volts, supply voltage is converted to the phase voltage, that is equal by root 3 star connected, then 231 volts the phase voltage. Now armature resistance 0.3 ohms for phase value is directly they given, and synchronous reactance also they have given, and power factor cos phi is also 0.8 leading. From this one phi we are going to calculate. Okay, the phi is equal cos inverse of this value, we are going to get 36.87 degrees. Now draw the diagram. Leading power factor, we know that V here, the V is leading this one by angle of phi. Based on this one we are going to this one. So from the basics, the line current IL is equal to 80 amperes, Now for star connection, so IL is equal to I phase. Line voltage is, line current is equal to phase current, whereas the voltage, the line voltage is equal to root 3 times of phase voltage. Now armature current for phase here is the same because it is connected in star. The impedance angle, that angle is equal to tan theta is equal to tan inverse of XS by RA. So here tan inverse is missed. Now tan inverse of this value 2.4 by 0.3, we are going to get 82.7 degrees. Now phi is equal to, we are going to nearly 37 and here is a 82. Combine, we are going to substitute the value. So what is the equation? Already we know that. So therefore theta plus phi, we are going 82.7 plus 36.87, 119.8 is the angle. So substitute the equation. The synchronous impedance is equal, ZS is equal root of RAL square plus XS whole square, this is a given value. So we are going to get 2.42 ohms per phase. Now impedance for drop, that is called ER, is equal to IA ZS. So 80 into 2.42, we are going to 193.6 volts, that is the resultant voltage ER. Now generated EMF for phase is equal to EB is equal to V square plus ER whole square minus 2 into V into ER into cos theta plus phi. Everything is known, simple substitution. So here what is the V is equal to, for phase 400 by root 3 231 whole square plus, so ER is equal to IA into Z, here 193.6 for phase values minus 2 into V into all values we are substitute. Angle we are going to get, so we have got theta plus phi is equal to 119.72. Simple substitution, so we are going to get, so 367.7 volts EB generated for phase. Now so line voltage EB is equal to root 3 times of this, then 637.87. Just you remember that. Actually our motor input is equal to 400 volts only, 3 phase, but in this one generated EB generated back EMF generated voltage is equal to 637.87 volts. You can observe nearly 237 volts is a more that. So already we know that over excitation here the EB is equal to greater than the V. Now this is only 400, this is a 637 volts. Okay. Now after that, so we are going to calculate this value. Okay, line voltage phase voltage we calculated into line voltage. So that is equal 637.87 volts generated inside. This is a required voltage. So whatever the data is given, simply written and written the formula. From the formula we substituted the given value, converted into phase values. Then we are going to get this value. Suppose I want in this case, I want sin alpha. What is the formula? Sin alpha is equal to, what is the formula generally? That is equal to, in over excitation, that is equal to ER by EB into sin theta plus alpha. Okay, theta plus phi. Now we know this value, we know this value, we know this one. ER also we know, EB also we know. We calculate from substitute the EB. Then we are going to get the sin alpha. The sin inverse alpha, so we are going to get the alpha also. Sometimes they will ask what is the load angle, what is the coupling angle. So from this one we are going to calculate the alpha also. Sometimes they will ask this also, what is the PM? So PM produced. So condition if resistance is negligible, R is very less the excess. Then we know the formula. What is the formula? that formula is equal to, so Pm is equal to, so E back EMF into voltage divided by XA into sin alpha, or so by substituting this value we are going to what is the mechanical energy developed in the motor also we can easily calculate. Okay. So if you know the basics, by applying the formula, just manipulation, we are going to get the results. Okay. So if the resistance condition is not given, then so write the same formula. What is the formula? That one, Pm is equal to Eb into V by Za cos theta minus alpha minus Eb square by Za into cos theta. Everything we know, Eb we know, calculated, and V is given, ZAV is given, and this angle also we are given here, and Eb also known, this one and everything is known. From this we are going to get what is the mechanical power developed during this period. 80 amperes drawing, 80 amperes for the load angle. At that condition, what is the mechanical power Pm is calculated by this one. From this one, if you are neglecting the subtracting the iron losses and friction and windage losses, we are going to the what is the original output of the motor also we can calculate if the values are given. Constant values are, constant losses are given. So subtract from Pm, we are going to get the actual net output, mechanical output generated on the synchronous motor we can calculate. If you know the mechanical output, we know the input. So output by input, we are going to get the efficiency of the motor also we can calculate. So these are all calculations based on the simple manipulation of these equations. I think you have some idea. Now let us do another problem. Here one problem is given. Same, here 10 HP motor is power is called, input power is given 10 HP, same 400 volts, star connected, same is a connected synchronous motor as a synchronous impedance ZS also is given. Find the induced EMF. EB is required, the line value, and angle of retardation. That angle of retardation alpha is required, to which the motor be excited to give full load output at a power factor is given, is the cos phi is equal to 0.866 lead. Now assume the efficiency also 88%. That means here the power output is given, you know the efficiency. From this one we are going to calculate the what is the input motor. So output by efficiency is equal to output by input. Now you know the input, require the input, then output by efficiency we are going to get the what is the motor input we know. So the motor input P is equal to root 3 VL cos phi in 3 phase. So from this one, you know you are going to calculate the armature current. If you know the armature current, then we are going to calculate the ER. If you know the ER, if you know the V is already given, from this one we are going to substitute the in formula. EB is equal to square root of V square plus ER whole square minus 2 into V into I into cos, here leading power factor theta plus phi. So here also we are going to calculate that theta is equal to tan inverse of x by r is given. Now everything is given. Simple, write the equation and do the calculations. Okay. Now do it here. Same, you draw the phasor diagram for avoid the confusion. Now 3 phase star connected, convert into phasor values. Output power is equal to 10 HP metric. 10 into 735.5 we are going to convert in watts, that is equal to 735.7335 watts. Now supply voltage is equal to how much? that is equal 400 volts. Now convert to the phasor value. By root 3 we are going to 231, and efficiency is equal to output by input, that is equal to 88% means 0.88. Now power factor is given 0.866 lead. Then find the phi, that is so cos inverse of 0.86, we are going to 30 degrees. Now motor input power is equal output by efficiency, substitute the value. So we are going to get, what is the value? So whatever the value that is equal, we are going to this value. Okay, that is equal to 8357.95 watts. Same motor input is equal to P is equal to root 3 VL IL cos pi. So in this case, we know the power input, we know the rated voltage, we know the power factor, we know the root 3. Substituting these values here, so here, so here you can see this P is equal to root 3 VLL cos pi. P already we known, substitute here, and VL is calculate already given, and cos pi also already given, and IL we required. So line current IL is equal P by root 3 VLL cos pi. Substituting the values, we are going to get nearly what is the line current. So what is the line current now? So 13.93 amperes. In this case, the IA is drawing 13.93 amperes from the supply with the leading power factor. Now for star connection, so we know that line current is equal to phase current is equal to armature current, that is equal to 13.93 amperes. We know the all phase values. Now synchronous impedance ZS is equal is given, and from that one you are going to calculate the what is the ZS, and at the same time you find the theta also. So we are 82.87. Now 30 degrees 82.87, we are going to theta plus, that is equal to 112.87 degrees. Now everything is available, all terms are known. Simple, put the formula, get the answer. So ER is equal to IA into ZS, so the resultant voltage, now that is equal to 39.31 volts. Now, so from the phasor diagram, so we know that by applying the cosine rule, same rule, that is equal EB whole square is equal this formula. So here, so V square plus ER square minus 2 into ER into cos theta plus phi, actually this phi is equal, previously we calculated both values substituting theta plus phi. Now here substituting the value 112, we have got it, so we are going to this one. Substitute the simple values, so EB is equal to 248.93 for phase values. I want the line value into root 3, we are going to get, so what is the value? So we are going to value root 3 into 248, nearly it will go above the 450 volts. So that is the line voltage EB, back EMF developed in the motor. Now at the same time they asked the alpha also. So for this alpha, you know the apply the sine rule. So by sine rule, so we are going to know that EB by, so here previously we have calculated all things. This is the EB, this is the EB, opposite this one angle. What is the angle? So theta plus phi. Now another is the V. So this is the ER. This is called alpha. So ER. So simple substitute opposite, that is EB by sine theta plus phi is equal to ER by sine alpha. I want this term. So simply going that side, so we are going to get all values. So EB by sine theta plus alpha, sine alpha, then sine alpha is equal to ER by EB into sine theta plus phi. So here ER knowns, EB knowns, from this one we are going to sine alpha. So that is equal 0.1455. So alpha is equal sin inverse of this value. So we are going to get what is the angle 8.37. That is the stator magnetic axis. Our rotor magnetic axis, the angle between axis angle difference is the 8.37 degrees centigrade at this condition. It's a maximum 90 degrees. Now only 8.37, both are coupled. Stator magnetic field and rotor magnetic field is coupled. It is running, but it is a loading angle is equal to 8.37. This is the value. Okay. So now these are similarly we can do the all problems. So what is the efficiency, what is the mechanical energy generated, what is the total energy generated in the machines, simple manipulations of equations. We are going to do the problems. Dear students, the practice makes perfect. You do the, I explained based on time factor, only 2 problems, but you have to do the nearly 20 problems. All problems are based on this simple exchange of equations. You practice it, you may get some idea. Okay. So what we have seen in this class? So performance of synchronous motor with excitation, normal excitation, under excitation, over excitation. At that condition, what is the back EMF developed? What is the load angle? We have seen. And at the same time, we have seen the power flow diagram from stator input to rotor output. How these changes takes place. How the electrical energy is given to the stator. From that, some copper losses is deducted, subtracted. Then input minus this stator copper losses gives the stator output that equal to the rotor input. That is we know PM, the mechanical power. From that, we are subtracting some friction and windage losses, some excitation losses, some iron losses. Then we are going to get the net mechanical output developed in the rotor, which is for the load. So these are the things. Thank you for listening my class. Practice remaining problems. If any problems face, then we will discuss in the next class. Thank you.